Okay, so couple announcements about the remaining lectures. So there will be class as usual this week. Right? Next week, Monday, there is not going to be a class. I'm going to have a makeup class maybe in the last of this second to last week of the semester. So Monday there is no class. Next Wednesday and the Monday after there will be two guest lectures. Usually I have one or two guest lectures in class. So I'm going to arrange for that. So the guest lectures will be on green computing and multimedia systems. Okay. So we'll bring two other faculty members who know something about these two areas to come and give a lecture. So material on the guest lecture is typically included as part of the class. So it's not like you can ignore it or just not come to class or anything like that. So do keep in mind that it's all part of the course. Okay, but it's good to have some other people come and give some different perspectives on what aspects of distributed systems they look at. Okay, so this time we'll do one on green computing, one on multimedia. Okay, and then we still have a class on World Wide Web and some case studies on DCOM and Corba and so on. There are still two core topics remaining, one on file systems and one on security. Okay? We may not get time to cover security because the lectures have taken me a little longer than usual to describe because I probably some talking more than what I usually do, or you guys are not talking enough one of the two. So I might have a compressed version of the security material, or if we just run out of time, I'm going to skip it. There is a graduate course on security that's offered on and off. So I don't spend too much time on that topic anyway. But if there is a little bit of time to squeeze it in, I will. Okay, so that's what is remaining for the course. Okay, so basically, file systems and security are the core topics, and then we usually have case studies, of which couple are guest lecture case studies. Okay, so that's sort of a roadmap of what is coming down the pipe. There is still a lab due this week, and there's the one more lab that is going to be handed out as soon as you turn that in. That lab will be due at the end of the semester. Okay, and as I had mentioned, I'll announce that again. Usually the final exam is a take-home exam. Okay, it is scheduled on the same day as the in-class final, typically, which I believe, as far as the exam calendar shows, it's on May 3rd. Okay, so I will hand out the exam on May 3rd. It's due 24 hours later. Okay, you don't have to come here. You just pick it up from Moodle and turn it back on Moodle. Okay, so it's all electronic. Okay, and the final exam obviously is, since it's take home, it's open book, open notes. You cannot talk to people, but you can do whatever you want in terms of Googling and all of that kind of stuff. Okay, all right. So, any questions on any of that? All right. So we will continue discussion from last time. So just to recap, we started this new topic on fault tolerance. Yeah, so we were talking a little bit about different kinds of faults that occur in systems. I spent a little bit of time talking about the Byzantine general problem and Byzantine fault tolerance, which is basically an extreme case of faults where machines can fail, machines can do arbitrarily bad things, and they can produce incorrect results, and how do you deal with all of that. So rather than going through some of that material in terms of recapping, I thought I will summarize it this way. Okay, so to deal with fault tolerance, you need to have replication. Okay, you need to ensure that if something happens to your service, okay, or data, then you have additional replicas to deal with it. Okay? And you can deal, so replication in this case, in case of faults, is dealt with in two slightly different techniques. Okay? Depending on what kinds of faults you want to tolerate. First technique is basically saying, of all the requests that are coming into your server, okay, split them across the replica. Let's say there are k replicas. When requests come in, just distribute the request to the k replicas in the normal case. Okay? And if one replica fails, then take all of its requests and then basically redistribute them among the remaining k minus 1 replicas. Okay? This kind of fault tolerance is, this kind of faults rather, are technique is relevant when you crash fault tolerance, when the machines fail silently. But we are assuming now that since only one replica handles each request, each replica produces correct results. Okay? This is by far the more common case of how replication is used in today's systems. Take any system that uses replication. Typically what is done is you take the incoming request, you distribute it among the replicas. If some replicas fail, then you redistribute the requests that were being sent there to the other replicas, so the service as a whole continues to function. Okay? So this is what is actually done in practice. So you only deal with crash fault tolerance. What we were talking about in last class was actually the second technique, which says send every request to all replicas. Every request is sent to every replica and they all process that request. They all produce responses. And then you are going to vote. Okay? These replicas are going to vote on what the correct response is. Okay? And you take the majority result. Okay? This is what we were talking about as far as Byzantine fault tolerance were concerned. We started talking about two-phase commit. That's also an example of voting. Okay? So in this case, every request has to be processed by every replica. So replicas are allowed to not only crash, but they are also allowed to produce incorrect results. Okay? Because there are other replicas that are functioning correctly, and so long as the majority continue to produce correct results, the voting will tell you what the right solution or right result is. Okay? So as I also mentioned, this is a harder problem to deal with because you have to send every request to all the replicas. That's more overhead, but it allows you to handle this more general case of fault tolerance, which is Byzantine fault tolerance, which arbitrarily bad things can happen. Machines can fail, they can have bugs, can produce bad results, and still we are okay. Okay? So although this is what we actually were talking about, as I mentioned, this is very expensive to implement. Okay? In practice, you need 2/3 majority, so you may need up to 3K additional replicas to handle K faults. Okay? So typically in practice, you never see this kind of technique, but for the purpose of the course, it's good to understand how these techniques work. Okay? So send request to all replicas, vote on the result. So that's where we are. And as I mentioned, this is what is actually used in practice. Much simpler. Do not send all requests to all replicas. Send it to only one. Okay? And if if some replicas fail, redirect the remaining request to the rest. Okay? That's basically what is done. So that's the high-level message you want to keep in mind. Okay? Because I didn't want the details to get mixed up with the concepts. So just to recap, we were talking about two-phase commit as an example of voting. Okay? The assumption here, this is used, as I said, in distributed or replicated databases. Every query is sent to all the database replicas. Database replicas are going to execute the transactions and they are going to vote, okay, whether we should commit or not. Okay, notice that in two-phase commit, you are not actually comparing the results yet. Okay, so this is only voting on whether to commit or not commit. Yeah. You may separately want to have a scenario where you actually vote on the result to decide whether you want to commit or not. That is not being done here. You are just voting on whether to commit or not. Okay. And as I said, that's a very simple process. There's a coordinator. Coordinator asks all the replicas what to do. Okay. Replica says vote saying commit or abort. Everybody says commit. You go ahead and commit. If anyone says abort, that's like a veto. So you can basically abort the transaction. So there are two phases. The first phase, the replica sends, coordinator sends requests to vote, and then depending on what the results are, you will vote to abort or commit. Okay, and this is what is the state transition diagram of each of the processes of the replicas. Okay. Note that what we want is safety, which means you never want a scenario, okay, this is all or nothing, this is atomicity. You don't want a scenario where replicas all voted to commit, but then some have committed, others have aborted, or vice versa. If anyone voted to abort, you don't want some to commit. The results always have to be the same. Okay? And I was talking about what happens if the coordinator crashes in the middle of the vote. I said you have to block. You can't arbitrarily take decisions and decide to do something without the coordinator telling you. Okay? So two-phase commit is safe, but it has this blocking property which says if the coordinator has failed, then all bets are off. Then all the replicas are going to block because they cannot proceed without the coordinator. They cannot tell you what the results of the vote were. Okay. So that's a blocking property, and to deal with that blocking property, you have a generalization of two-phase commit called 3PC or three-phase commit. Okay. And what is done here is we have added a little more detail to the algorithm. So voting is, there's going to be three phases of voting, not two. In the previous case, there was a voting phase and there was a results phase. Here, there will be three phases. And the reason we put the third phase is even if the coordinator commits, by adding this phase, we will basically be able to make a decision without the coordinator. Yeah, that's the idea. You don't want this bad blocking property where there is no progress. That's called the liveness property of a distributed system where you want to make some progress. Safety property basically says you don't want something bad to happen. Okay, the safety property is satisfied, but at the expense of you cannot do anything bad if you do nothing. Right? So the previous algorithm took the approach saying if you don't know what to do, do nothing. That way nothing bad can happen. Okay? But that prevents you from making progress. You are blocked on waiting on the result. Okay? So what is done in three-phase commit? So this is again the coordinator, and that's the state transition diagram of each replica. Rather than going through that detail, let me explain in words what is going on. So voting is going to take place in three phases. Coordinator is going to kick off the voting saying, what would you like to do? Abort or commit. Okay? Each replica is going to vote whether to abort or commit. Like before, if everyone says commit, then the decision will be to commit. If anyone says abort, one or more say abort, okay, then you will abort. Okay? But so the coordinator will tabulate the results. But rather than telling the replicas go ahead and commit or abort, it is going to just tell them the results of the election and say send me an acknowledgement that you received the results. Okay? So basically you will say that, or at least if the decision is to commit, you will basically say prepare to commit. Okay? If it's abort, then there isn't much you will do, you'll just say abort. But if you want to commit, you're going to say the results of the voting were to commit and acknowledge that you received this message. So you will send that to every replica. All the replicas will say yes, we received the message. And after you know that every replica has received the message to commit, then you will say go ahead and commit. Okay, so it's a two-step process where you will tell the results of the election and then say go ahead and do the right thing. So that's basically what this entire diagram is actually showing. So you after you vote, you go into the ready state to wait for the results of the election. And if the results were to commit, you will basically be told that your decision has been made to commit, acknowledge. So you will go into what is called a pre-commit state and wait for the final go ahead from the coordinator. Only when you say go ahead will you actually commit. So commit takes two steps. Okay? If the decision was to abort, you are going to abort directly. Okay? Now, rather than looking at the state transition diagram, you may want to think, what did this give us? What have we bought by adding some more steps to this algorithm? Okay, it's still voting. Okay, in the end, you are going to vote for commit or abort, and based on the results, you will do the right thing. Okay? But we are trying to avoid this property where if the coordinator crashes, then you may not do the wrong thing. You may do the wrong thing. You want to avoid that property. Okay, so what is the right thing to do here? So what did this give us by saying, let us go ahead and do this in two steps rather than one? Okay, so what are we trying to do? We don't want the replicas to block if the coordinator crashes. Okay, neither do we want anyone to block if a replica crashes, but we'll put replica crashes aside for a moment. Let's only take the case where the coordinator crashes. Okay? So we can assume that the coordinator can crash anytime during the voting process, and still we want to be able to do the right thing. Okay, so let's take the case where every replica has voted to commit, okay? And then the coordinator crashes after telling them the results of the vote. Okay, so where are all the replicas? Okay, the replicas are in pre-commit state. Okay, if the coordinator crashes and you never hear from the coordinator saying go ahead and commit, you've only been told the results of the election, can the replicas proceed without the coordinator telling them to go ahead? if the coordinator crashes?
The coordinator may not have committed.
Coordinator may not have committed. That's okay. That's fine. When it recovers, it will have to do the right thing.
Already knows that everyone else has agreed to commit.
Yes.
So they can go ahead and commit.
Okay, so let's see that, let's say coordinator crashed and the replicas are sitting there, what should we do? Okay, so they may ask each other saying, did you hear from the coordinator? Okay, let's assume that at least one replica has received the pre-commit message. Okay. If no replica has heard anything, they will still be all in the ready state. That you should be clear. If the replicas have not heard of the results of the election, you are in the ready state. Okay, if you are in the ready state, you say, what should we do? What's the safe thing to do? Safe thing to do is abort, because you can say, we did not hear from the results of the election. Let's just play safe and abort a transaction and restart it. Okay? And that's okay, because no replica has actually heard from the coordinator, so they can go ahead and abort. Okay. In two-phase commit, you could not do that, because what might have happened is, remember, the coordinator is also voting. So what may have happened is the coordinator may have also voted, okay? And if everybody had actually voted commit, it may have gone into commit. Here in the worst case, the coordinator will actually be in the pre-commit. It wouldn't have committed. So when it recovers, it can, if the others have aborted, it still has a chance to abort the transaction, okay, which you could not have done. So if you're stuck in the ready state, go ahead and abort, no problem. Okay, that's a safe thing to do. Now, if you are stuck in the pre-commit stage, what can the replicas infer? The replicas will infer that if the only way we could have gotten in the pre-commit stage is everybody voted to commit. And that's what the results of the election was, and this is why you got the pre-commit message. Okay? If that is the case, it's fine to go ahead and commit, because you know the results of it. You can automatically infer what the election result was here. So you can go ahead and commit the transaction, and that's okay. You won't have a scenario where the coordinator I'll ask you to go into pre-commit and it has aborted. That will not be the case. It will also be stuck in pre-commit when it crashed. Okay, so when it recovers, it can actually go ahead and commit as well. Okay, so what we want is, we don't want some replicas to commit and some to abort. Okay, so this is basically by adding this extra state here, okay, you can infer what the results of the election. If this state was not there, as in two-phase commit, and you only have the ready state, you cannot infer the results of the election, because you have to actually be told by the coordinator what to do. In this case, if you are stuck in ready, you don't know the results, but you say, I am going to be safe and abort, and that's okay. Okay? And if you are in pre-commit, you do know the results, so the replicas can actually move ahead without the transaction, without the coordinator, and not be blocked. Okay? So this is basically a generalization of three-phase commit, where if the coordinator crashes, processes will not block. Okay? So it's a variant that avoids blocking. It does the same thing in terms of voting and trying to figure out what to do, but we have gotten rid of the blocking problem of two-phase commit. Okay? That's a very classical algorithm in databases, two-phase commit or 2PC, and it has this well-known blocking problem, and by adding this one state, you can get rid of it.
If the coordinator, if the decision is to commit and the coordinator commits before sending the pre-commit messages, and like nobody received the pre-commit messages and they abort.
Okay, good question. The question is, what happens if the decision is to commit and nobody has received the go ahead and go to pre-commit message, and what the coordinator commits? This is the state transition diagram of the coordinator as well. Okay? So the coordinator cannot take the results of the election and directly commit. It also has to go into pre-commit. Okay? So if you follow this algorithm, it says, I am the coordinator, I just get the results of the election, I tell everyone to pre-commit. Okay, even if they don't actually receive that and you crash, you would never have committed, because you would have to go here, you have to send the next set of messages, only then you can commit. So the scenario you mentioned will not happen in three-phase commit. It can, however, happen in two-phase commit. This is why we could not do. That was exactly the problem in two-phase commit, where you get the results of the election and you send the messages out. But before any message has gone out, you crash, but you could have actually committed. So if nobody has received a message and you're stuck in ready, you cannot even make a decision to abort at that because the coordinator could have decided to commit. Okay, so that's why you are stuck there. Okay, here you will not be stuck because in the worst case, you will actually be here. Okay? And if everyone else decides to abort when the coordinator records is still in pre-commit, you can go and see if anyone has actually committed or aborted. You can check that, and then if you want, you can abort or commit.
So coordinator waits for the acknowledgements from all the replicas before, like.
Yes, coordinator has to wait for the acknowledgement. Yes, question.
If half of the replicas are moved on to pre-commit and half of them are in ready state, then when the coordinator goes to half of them will come in and half of them will go to.
Yes, good point. So these are all scenarios you actually have to take into account to convince yourself you're right. So it may be that half of the replicas received the pre-commit message, the other half did not receive it, or before they received it, coordinator crashed. Okay? So some replicas are hanging in pre-commit state, some are in ready state. Okay? So now if they have to make a decision without the coordinator, they have to do exactly that. They have to ask each other. If any one of the replicas has received the pre-commit message, the others will be still stuck in ready, but they can infer the results of the election. Because if even one received it, you know that the only way you could have received that is everyone voted to commit. So they can then ask one another and go into the pre-commit stage and then commit. Okay. There's always a path to one of these two final states. Even if half of them have received, half of them are not received. No matter what the crash scenario is, there is still a way to figure out what the decision is and make the right decision. If nobody received that pre-commit message, they will all be stuck in ready. And we say it's okay to abort. Okay, the worst thing that could have happened is we all voted to commit, but before we got the results of the election, the coordinator crashed. So the worst thing is coordinator is stuck in pre-commit. We are all stuck in ready. We will abort. When the coordinator comes up, he's still not committed. He's still stuck in pre-commit. So the coordinator can check what the other replicas did, and there is still a wait for the coordinator to abort at that point. Okay. So there's always a way to make a decision, even if any, and the same thing, I have not argued what happens when replicas crash, that the coordinators and the remaining replicas can move ahead. Okay. So there's always a way to make a decision and it be safe. Yes, question.
What is the external stimulus for a replica to go from pre-commit to commit if the coordinators crashed or not crashed? So does the coordinator send an explicit message for the...
Yes. If typically there is no crash scenario after the pre-commit, you will get another message from the coordinator saying go ahead and commit. So you'll get this global commit message. And then you send an acknowledgement and you transition into it. Okay, if the coordinator crash, this won't happen, so there will be some additional message exchange which is not shown here that the replicas can figure out what to do. Okay?
So how is liveness guaranteed if all the replicas are in pre-commit state and coordinator keeps on crashing?
Okay, how is liveness guaranteed? If all the replicas are in pre-commit state, coordinator has crashed, you will not get a global commit message. Okay? You can always run leader election again, elect a new coordinator among this. That coordinator can ask, did anybody receive pre-commit? Is anybody in pre-commit? If you are in yes, then the new coordinator knows the result and it will tell everyone to commit. Because the only way you are in pre-commit is that that new coordinator will guess that you all voted to commit. That's why at least one of you is in pre-commit. Otherwise, you would not have landed there. Okay? So you can always rerun leader election, elect a new coordinator even without the original one and make decisions.
And this is not possible with a two-phase commit because you've already committed. That time you cannot run leader election and then see who has committed and who is not committed.
Right. So if you are actually in two-phase commit, if the coordinator crashed, everybody is stuck in ready and you run a new leader election algorithm, you do not know the results of the vote. Okay? Because you do not know what the coordinator itself voted. Because the coordinator is one of the replicas. You can ask what the others have voted. Okay, they may all say commit, but that still doesn't tell you what the coordinator voted. Okay, so and you cannot even go ahead and abort because if you all voted commit and the coordinator voted commit, the coordinator may have actually committed the transaction and crashed while these messages were going out. So coordinator may end up in a state where it has already committed. So if you even abort saying, let's just not worry about it and abort, that may also be the wrong thing to do. Okay? So there are some subtleties here to keep in mind. Okay? And again, as I said, we only looked at the coordinator crash scenario. The same kinds of arguments apply when you think about a replica crashing and not being able to vote. There's still a way. In this case, you will be stuck in three-phase commit at least you can go ahead and figure out what to do. Okay, because there's always going to abort is always a safe thing to do. Okay, so that's an option that's available if some replicas are not able to vote, which you could not do in the other case. Okay. All right. So that's 2-phase and 3-phase commit. As I said, classical techniques from this databases that involve voting. There is a class of algorithm called consensus algorithm or Paxos algorithm, which I have not covered here, that allow you to also look at the results of a request and decide what to do. Okay. Here we just asked each coordinate, each replica, what would you want to do? Okay. Typically, if you want to do full-fledged for Byzantine fault tolerance, you will say what were the results of your request. Okay, so you send the response, you compare the responses, and then also decide what to do. So the voting phase actually involves comparing the results and then deciding whether which result is right and which result is not. That technique is class of technique is called Paxos, which we will not cover here. It's a fairly complicated algorithm, so I'm going to not cover it in this class. There's a paper I've put up on the reading list if you want to go look at it. It's somewhat mathematical, but it does give the technique there. Okay, so I'll just mention that technique and move on here. Okay, so so thus far we have talked about voting and what happens when some replicas crash, etc. There's also this other side of fault tolerance, which is what is called recovery, which is what should be done if a crashed server comes back up. Okay, what are the steps to perform so that it can rejoin the group of replicas and start doing useful stuff? Right? Typically, the assumption is that when a replica crashes, it could be down for an arbitrary amount of time. Okay? Other replicas may have gone ahead without it and done additional processing, so they may have more information or more state than this new replica that crashed. Okay, so whenever a replica comes back up, it has to resynchronize itself with the remaining pool, so it has caught up with the rest of the replicas. Then it can proceed from that point on. Okay. Typically, that process is called recovery, which is resynchronization. In databases, the way this is done is all the replicas actually keep a log of the request they have processed. Okay. So when a new replica comes up, it can just ask one of the replicas saying, send me a list of requests you processed while I was down. So you get the log, and then you simply process that log. Okay. You just simply replay that log and you catch up. Okay. So you have to keep track of what requests were received while some replica was down, and then replay those requests or reprocess those requests so you catch up. So that's one way of resynchronizing. Another way of resynchronizing is through checkpoints. You can periodically take checkpoints, have replicas take checkpoints. So when a replica comes up and says what happened while I was down, you say here is the checkpoint that tells you all the state that you missed. So you just load that checkpoint and you caught up to the previous checkpoint. Okay, so you can essentially use checkpointing as a way to resynchronize. You can use log replay as a way to resynchronize. Because there are two ways to actually recover, which is one is checkpointing, which is you keep a copy of all the state and you reload that state. Another is you keep a log of requests and you reprocess all the missed requests. Okay? So these two techniques are complementary. You can use either one or you could use both. Okay? You can reload the last checkpoint and replay all the requests that have been seen since the last checkpoint. Because the last checkpoint only allows you to recover till that checkpoint point in time, but additional requests may have also been processed. So typically you will do a bit of both. Okay. So here is, we know how to do checkpointing. Remember when we did distributed snapshots, we essentially talked about how to take a consistent cut and just checkpoints and so on and so forth. Okay. So this is basically, we are not going to spend too much time on this, but this figure shows that periodically you will take a checkpoint. All this figure is saying is if the checkpoints are taken independently of one another, you may not have a consistent checkpoint. So you may have cascading rollback saying, is the previous checkpoint consistent? If it's not consistent, based on the definition of consistent checkpoint to use, then you say that is a useless checkpoint because the coordinators of the replicas didn't coordinate with one another. Right? Then you may roll back to the previous checkpoint and is that checkpoint consistent and so on. Okay, so you may actually have this cascading effect. So the right thing to do is, of course, to use the distributed snapshot algorithm That way every checkpoint is consistent. You don't need to assume clock synchronization or any of these things. Okay, so you'll automatically get a consistent checkpoint. But if by any chance you do not use such techniques, then before loading a checkpoint, you better make sure it is consistent with respect to the state of the computation. Otherwise, you'll land yourself into trouble. Okay, so message logging I talked about already, so I'm not going to say much in terms of logs and so on. Right, so that's the end of that discussion on fault tolerance. Okay, so it was sort of a brief discussion. So just to recap, replication is the technique that is used to ensure that faults can be handled. Depending on what kind of faults you want to handle, you will use different kinds of replication. If you want to simply handle crash faults, which is machines fail, but when they are up, they produce correct result, you just need k plus 1 replicas. Okay, to handle k faults, so whenever the machine fails, the other replicas that are up will take over its work or burden and things continue. If you are Byzantine faults, then you need to actually vote on the result because the results can be wrong. Not in crash fault tolerance, whenever you produce a result, the result is assumed to be right. And the system is not buggy. Crash in Byzantine fault tolerance, you can produce wrong results. You can also crash, but you can produce wrong results. So to prevent wrong results from going back to the end users, you have to ensure that a request is processed by multiple replicas and vote. Right? So two-phase commit, three-phase commit were just examples of voting-based algorithm. Okay? There's a even more complex technique called paxers that also do the same thing. So that's sort of a 4 or 5 sentence summary of that entire chapter. Okay, so what I'm going to do today and next time are essentially switch gears a little bit and do 2 case studies. Okay, one today is going to be on data centers and cloud computing, and next the class case study is going to be on World Wide Web. The reason I am actually doing this slightly out of order, this is typically done, I guess, 2 or 3 classes from now. But the reason I'm doing this is this material is going to be useful for the last lab. Okay, because we are going to actually run the last lab code on the cloud. So to know what to do for the lab, you need to know what cloud computing is and so on. So I'm going to actually talk about that today just to build up material for the lab. This is a self-contained topic, so doing it out of order doesn't have any implication on the remaining lectures we have. Okay, so let me start with what is a data center. So the topic has 2 parts, data centers and cloud. And so we'll do the data center part first and then the cloud part next. Okay, so we have to start with what is a data center. Okay, so data center is essentially a facility, okay, where it basically provides lots of servers and lots of storage for some kinds of distributed applications. Okay, so these are referred to as server and storage farm. Farm essentially means a facility with lots of servers and lots of storage. Typical data centers may have 1,000, tens of thousands, hundreds of thousands of servers. Okay, they could be very large facilities, so they may be used to provide service to lots and lots of applications or single very large application. Okay, so they may have very large amounts of storage and very large amounts of computation. Okay, so you can ask who uses data centers. So data centers are commonly used by any company that needs to run IT applications. They are used by companies that provide consumer-facing applications. Okay, so practically every company runs its back-end applications, whether it's to do payroll processing, whether it's to do HR, whether it's used to do any of the businesses of the application. So if you take UMass, for instance, your Spire is an example of an enterprise application that does course registration and student enrollment. All of that is handled by Spire. Okay, there are payroll applications and so on. So all of these applications are hosted on some server somewhere. Okay? These servers are actually placed in a data center. In this case, probably the data center is small. It's not going to be having 100,000 servers or anything like that. But if you look at some of the biggest data centers, like you can look at data centers owned by Google or Facebook or Amazon, eBay, those data centers tend to be very large. Yeah, because like if you take Google search engine, for instance, that is a global scale application. It services probably billions of requests every second. You can't run that search engine on one machine. Neither can you even run it on a single data center. In that case, that service is spread across multiple data centers. The computational needs of such applications are so large that you need very large data centers for it. Yeah, so in lots of internet-facing companies use data centers, and they build the biggest data centers today. Okay, Google, Microsoft, Apple, Facebook, they all have very, very large data centers. I'll talk a little bit about that as well. Okay. So typically, data centers or the servers and storage, they run applications that do data processing, that can run very large web-based applications, or they'll run business applications. Aspire is an example of a business application. Okay, it's not available to the entire world, it's only available within an enterprise or a university. Okay, so the reason this has become an interesting topic recently is the sizes of these applications that run on data centers has continued to grow, mostly because of this the rise of these internet-facing applications, like Google, Gmail, Facebook. These applications have come about and they continue to grow in popularity. And the sheer processing and storage needs of these applications have dominated sort of how data centers are built. Okay, we'll see that some data center designs are actually influenced by application needs rather than vice versa. Okay, so data centers have been around for decades, okay, but sort of what we call the traditional data centers, where what we call what we refer to as a static architecture. Okay, you had this pretty boring IT stuff where you had a machine room filled with servers. Then you will have some applications, and the administrator will say, let's run this database on this server, I'm going to run the website on that server, and some other application on a third server, and you're done. Okay, the machine, these are mapped to applications are mapped to machines, and this is a static mapping. And then you use some sort of a storage area network or some storage facility to provide storage to this application. Okay, but what has actually happened today is data centers have become very dynamic. And the reason for that is the workloads that are being seen by many of these applications see lots of fluctuations over time. Well, the workload can suddenly spike, it can ebb. So the workload is not static. So what that means also is that the way the application is designed and architected also has to deal with this dynamics. Okay, so if the workload goes up, the data center should be able to respond on the fly and automatically by allocating more storage or more computational resources to that application. Right? Because users don't want to see a message saying the server overload, try again later, which some sites still do. You may have seen these kinds of messages. Okay, that's not a desirable thing to show to your user. Okay, you can't say Spire is overloaded, try again later. Okay? There was a time a few years ago when they did not actually do a good design of the Spire registration system, and this actually happened. Okay, during pre-registration time, server got overloaded, Spire went down. Okay, then they said, if you are a graduate student, you can register from 9 to 5 on Mondays, and if you are a senior, you do it on Tuesday. They actually had to do things like this, okay, just because the system could not handle the load, okay, which was really a bad design that increased user inconvenience. Okay, you don't want these kinds of things to happen. If load goes up, you should be able to seamlessly say, here are 4 more servers, and now spread the load across the server. Start some more replicas and then just partition the load and things should be fine. If you design the applications that way, then you should be able to handle these kinds of dynamics. But for that, the data center also has to be designed in a way that allows these kinds of resource allocation. Most of it you want to automate, not do manually. Yeah. When I talk about cloud, I'll show some examples how you do this automation. Okay, so I just wanted to put a picture of what some data centers look like. So this is basically an aisle of servers. Okay, these things here are racks. Okay, so you have a rack, okay, and you have the servers that actually are stacked one on top of another. So there is a server that is, you can see a stack of server on a rack. And if you go into a data center, you just see aisles and aisles of this rack. Okay. If some of you come to this field trip that we have been planning to go to this local data center in Holyoke that UMass has built, you will see exactly this. There are lots of aisles of racks. And each rack will basically have servers on them, okay, and storage capacity. So that's what basically, and these data centers can be very large. Okay, some of the largest data centers will be 10 times the size of a soccer field. Okay, so just to give you a sheer size of scale. So it will be sort of a very large facility where you have acres and acres of these things sitting inside the data center, just because you need to have space for 100,000 cores or servers in one data center. So basically, you have the main components of a data centers is you have racks of servers and your storage. Right? Now to ensure that you can run this data center, there are a lot of other equipment that you have to put. Okay, first you have to put networking equipment. All the servers are networked, so the network architecture you will have lots of network switches and routers and all of that kind of stuff to go with that. But the other two things that you also need is power and cooling. So you'll see lots of interesting things being done to deal with the power infrastructure of a data center. Okay, so typically there will be multiple redundant layers of power. You cannot have you cannot afford to lose power for 100,000 server facility. Okay, then like entire systems may go down. Okay, so what is typically done is each of those racks or server will have a battery backup UPS, an uninterrupted power supply. So if there's a local outage of some sort, then that rack can still continue to function. Okay, that's one. Now, if there is actually a global outage, some power that is being supplied by the electric company itself goes down, then you may actually have diesel generators that will kick in. Okay? So typically, whenever there's an outage, all the servers will switch over to the UPS. UPS capacity may be few minutes. These are batteries that can keep the server running maybe for 5 to 10 minutes. After that, the battery will get exhausted and the server will go down. So that is the window you have to do something and bring power back on it. Typically, what is done is then you start your diesel generator that will generate local electricity and keep the servers running. Okay. So you have these multiple layers of redundancy. Many large data centers will also have connections from multiple electric companies. So if one company has an outage, you start receiving power from another company. Okay. So you have all these layers of redundancy built in just to ensure that power does not go down. Okay. So that's basically the power infrastructure. The cooling infrastructure is another very important issue for data center. Okay. So if you think of all these aisles of servers and think of what happens when they run, all these servers generate a lot of heat, okay, because they are consuming power. Okay, the disks are spinning, the CPUs are computing, and so the servers actually tend to get hot, and they need to be cooled. Okay, so there's a lot of emphasis on how to cool these servers efficiently. Okay, so there are a lot of innovations done on that front. So what would typically happen is you would actually pump in cool air into the facility. So each of these racks will have cold air actually being pumped here. And the air enters the server, okay, and it takes the heat, and hot air actually goes out from the back of the server. Okay. And then this hot air is taken out by fans, and then they're sent out to be cooled, and then the air conditioners or chillers or whatever you have will convert that back into cold air and pump that. So you have this air circulation that is used to cool this server. Now that might seem like a trivial task, but if you actually look at the numbers, you will see that the electricity cost of cooling the servers, typically in many cases, can be as much as powering the servers. Okay, so if you spend, let's say, $1 a month of electricity to keep a server on, it may actually take you another $1 of electricity to cool that server. Okay, so basically the server generates so much heat that in some less efficient data centers, your electricity bill doubles because the air conditioning cost is as much as the cost of keeping the servers on. And the reason all of this is important is if the typical electricity bill for data centers can turn into tens of millions of dollars a month. Okay, so if you get an electricity bill every month, that's a year, $5 million. Okay, you want to somehow do something to keep that low. Okay, it's not like paying $50 a month for your home electricity bill. So the cost of powering the data center is actually quite a lot. Okay? And that has nothing to do with the money you spend on buying the server to begin. That is another large cost. But the cost of running those servers is also very high. Okay? So these are all very important issues as a result. How do you keep the machines running so there's no outages? How do you keep the machines cool so they don't overheat and melt or some such thing? Bad things shouldn't happen. Okay? Now, the rate at which some of these online services have grown, like Google or Apple or whatever, all of these services, these companies have to constantly build additional data center capacity because the number of users for these services keeps on going up. Okay? So the servers you have are no longer sufficient to keep powering or keep servicing the users. Okay, so you will see always press releases saying Apple is building yet another gigantic data center somewhere, and Google is building 3 new data centers, and this time they'll build it in Europe to service the Europe users and so on. Right? And the cost of building these data centers runs into hundreds of millions of dollars for each large facility, and you have to keep on building them. So people have thought about how do you build data centers more efficiently, rather than building a gigantic facility with lots and lots of power. Can you do this in a more modular fashion? Okay, so there has been this entire design of what are called modular data centers. Okay, here is a picture of a modular data center. You'll see that it's all open. So what a modular data center is effectively, rather than having a very large room and putting racks of aisles of racks rather, and putting servers, you do this in a smaller modular way. Okay, so what you do is you basically put your machines not in large room but in large containers. Okay, so if you look at a 18-wheeler truck that you may have seen on the highway, that's an example of a 40-feet container. Okay, what's basically what is on the truck is essentially a 40-feet container. So the way some of these things are designed is you take a 40-feet container, one of them is shown here, okay? And you instead of put one aisle of racks in there, okay? And the servers are pre-installed in that rack. So rather than calling up your server company and saying send me 10,000 servers, you will say send me 100 of these containers pre-populated with servers. Okay, so the goal is basically this container will show up on some truck. Okay, you will unload it and you will basically stick it there. Okay, and then you will just what this will have is it will have a place to connect electricity, place to connect network, and a place to pump air. Okay, and you basically just plug in electricity, network, air. Okay, and then the machines are already pre-installed. There is nothing to do. Okay, and basically the machines come up and you can start using the machine. Okay. So you can now extend the data center capacity in granularity of 40-feet containers, rather than saying build another 10-acre facility and we'll put another 100,000 servers there. You can keep buying this container. So this is actually a schematic of a real data center. It's not a picture, it's a schematic of a real data center that's been built in Chicago. So you will see that this is where the compute and the storage sit. Those are the chillers that pump cold air. And then you just have electricity and network going in. And if you open one of these containers, you'll just see an aisle of racks in there. Okay, now, the vendor is selling you, rather than selling you individual server, they're selling you containers of machines. Okay, so they have pre-installed the machines and the whole set of machines just shows up. Okay, and then you don't have to unbox machines and think about you built a 100,000 server facility, how many boxes you have to simply unpack in order to install it. Right? Because machines will come in boxes. Right? So and then installing is a big overhead. It takes sometimes up to a year just to install machines in this large facility. Okay? So even after everything has been constructed. So all of those costs have gone down because you are just buying this modular data center. Okay? So each container, so it's more plug and play. You just add electricity, network cooling, and you are done. Okay? So you can pre-assemble data centers in a cheaper fashion if you do this kind of stuff. Okay? So many data centers no longer look like this. They have started looking like this. This is the most modern design of data centers. Not quite taken off, but many large companies are starting to do this stuff. Okay? So you can go to Dell or HP and say, give me a container, okay, rather than saying, give me 50 servers. So that's the kind of things that people are looking at. Okay? Now, the one thing that most of these data centers will use that is common, that allows them to be dynamic and so on, is to use virtualization. Okay? We talked about virtualization, I think, in lecture 4 and 5. Practically every machine, every server in your data center is virtualized. Okay? And the virtualization is going to allow us to do interesting things on these machines. Okay? So first thing it will do is it will allow a server to be sliced into smaller virtual server. Okay? Each server may, let's say, have 16 cores and it may have lots of RAM. Okay? So you don't put a single application on this large server. What you will typically do is you may partition this server into 4 smaller virtual machines and say each virtual machine gets 4 cores. Okay? So you've taken one large 16 core servers and made it look like 4 quad core virtual servers. And then each of those virtual servers can run its own operating system, own applications. So this would be type 1 hypervisor, just as an example. Okay, so you'll run these type 1 hypervisors on these virtualization modules, and then you'll run virtual servers, and then OS and applications will run on these virtual servers. Okay. Now the advantage of virtualization is that it allows us to do interesting higher level optimization. Okay. If a machine gets overloaded here, okay, you can use the virtual machine hypervisor to give it more cores or more memory on the fly. Okay, this is what virtualization layers allow you to do. You can resize a virtual machine. Okay, so if this is a dual core and this Windows here is got overloaded, you can just increase its size, give it one more core from that server if such a core is available, is not being used. Okay, so here's a third core. And now suddenly that virtual server has more computation capacity than before. If its server was maxed out, now you have more CPU. Okay? Or you can give it more RAM. Okay, so you can rapidly readjust the allocations to virtualization. This is one key advantage of virtualization. Okay? You can also move virtual machines within a LAN using what's called migration. Okay, we talked about, when I was talking about process migration, you remember I said you can also move virtual machines. Okay, the entire virtual machine can be moved from one server to another. So you can remap which virtual machines run on which physical server on the fly, depending on whether some machines get overloaded or some machines might be, you may need to take a hardware server down for maintenance or whatever. You can migrate them within your data center. Okay, this is very easy. Yes.
Yeah. It's also very easy to deploy multiple VMs of the same type to scale up an application too.
Yes. It is also easy. Virtualization allows you to create one image and say bring up 10 virtual machines that use the same image. Image is basically, think of it as a virtual disk containing an OS and application. Okay, so you can just boot up multiple virtual machines using the same image. So there are lots of interesting things you can do once you have virtualization. And that's basically the reason why all these data centers are virtualized. Okay? So are cloud platforms which run on data centers, and I'll talk a little bit about that in a few slides. Okay, so there is a little bit of animation here which shows that VM has gotten overloaded. So now you basically can move it to move that small VM here, and then this VM you can then take that and give it more resources. Okay, so there are multiple virtualization platforms, and I just have a few named here. VMware you probably heard of. There's one called Parallels. In the open source world, you will have VirtualBox and Zen and KVM that all allow you to do similar things. Okay, so just to give you some flavor of the server virtualization technologies that are out there. Okay, you don't need to know anything about them, just to know that these kinds of the systems exist. Okay. Now, there are different kinds of workloads these data centers can run. I have been talking a little bit about server workloads, and that's shown in this picture where there is essentially a rack of servers, and this is sort of an expansion of a single server, can have multiple sets. So 6 virtual machines, each virtual machine has its own OS and own application. That's basically what is shown there. Okay. That's one typical scenario for using a data center. Okay, here's another scenario called virtual desktops. I don't think most of you have heard of a virtual desktop, but let me explain what it is. Okay. A virtual desktop essentially says, rather than having a laptop or a desktop for every user in your company, give them what is called a thin client. A thin client is a low-end client. Okay. It could be, let's say, just a simple tablet. Okay. Or it could be a netbook, a low-end machine. Okay. But since the user may actually have to do higher-end computation, what you will do is you will actually also give them a virtual machine that is sitting in some remote server. Okay. This is effectively your PC, your desktop, but hosted inside a virtual machine on some remote server. Okay. So typically what you will do is you will take your thin client like a tablet or a low-end machine, and you will connect to that virtual machine, okay, using VNC or remote desktop technologies. Okay. And essentially it will look like that machine is local to it. Except that your desktop is essentially sitting on a virtual machine in some data center. Now, this is another use of data centers where rather than putting your server applications onto the data center, you essentially move the entire desktop into the data center. Okay, this is also referred to as thin client computing. Okay, if you actually read papers in distributed systems, you'll often see reference to fat clients and thin clients. Fat clients essentially means I have a powerful laptop and everything, all my stuff is on the laptop itself. All my data is on the laptop, I can do local computation. Thin client basically says that I have very little state here. All my data is somewhere on a server and I'm simply using my client to connect to that server and do remote computation, remote application. So you can use this to do remote application. Now this is very useful if users don't have to do heavy duty stuff, right? If you think of, let's say you go to a grocery store, okay, at the checkout terminal, you will see that they essentially have a desk PC there. They're using that to scan your goods and then print out receipts and process payments and so on. Okay. Now those kinds of applications don't need heavy duty PCs. Yeah, they typically need a lightweight desktop to run that single checkout application. Even better way to do it is you actually don't have a full-fledged PC there. You have a very low and thin client, and the PC is actually stored in a virtual machine somewhere on the cloud or maybe in a data center. And all that local PC is doing is it has a connection to the remote PC and it's just simply running the application remotely. The entire checkout application is actually running in a data center. What this does is it reduces. So you may ask, why do all of this? Right? Why not just give a $500 laptop to every user? Why put it all in some data center? That's a good question to ask. And the reason this kind of virtual desktops have become popular is it reduces maintenance overheads. Now think of, again, going back to this grocery store example, you may think of this may be a chain of grocery store. Each grocery store has 20 checkout terminals. Yeah? Now let's say new security patch came out because somebody came up with some malicious bug. So Windows or OS X or Linux, whatever the OS is, has come out with a new security patch. Now think of the IT guys who are administering these machines. Typically, they might actually have to go store to store and go and install this patch. Okay? This is a big overhead for these IT administrators. They have to physically drive to every store, every PC and do all of this maintenance. Okay? If they may have some automation, maybe they can install the patch remotely, which can also be done. Okay? But typically there are always headaches. Maybe the keyboard on something doesn't work or some software has crashed. You have to go and restart the machine. Checkout counter cashiers don't know how to administer the PC. Okay, so they have no idea. They are just using the application, somebody else's job to maintain. But if the entire state was stored in a data center, okay, then all the administration has become centralized. The administrators just have to administer that because there is very little stored on the thin client. Thin client just have a network connection and they are just connecting to the desktop inside a data center and doing all the computation remotely. So the main reason to have virtual desktop is this final bullet, that easier to maintain and easier to manage from an IT administrator standpoint. This is solely the reason why they have become popular. Okay, if it was just as easy to go and do this on every desktop, this would not actually be the case because people like to have local state. You don't want to connect to network because the network goes down, I can't do anything. Right? Yes.
Yeah, so maintenance issues and licensing updates are actually the reason why my undergraduate institution, WPI, switched to virtual applications for all of their labs.
Yes.
It makes it so much easier.
Yes. So I think if you centralize it using virtualization and use thin client, this is basically the advantages to it. Okay, so this is something to keep in mind. This is the only thing we'll say about virtual desktops in this course, but just do keep that in mind. That data centers also run desktop applications, not just server applications. Okay. So many challenges in data centers. So resource management is a key one. How to manage 100,000 servers effectively. How do you deal with unpredictable workload? What if the workload suddenly goes up? Okay, you're running an online store, say. You decide to have a sale. Okay, and then your sale becomes so popular that so many users come into your site, their site crashes. You don't want that to happen. Just at a time where you're making a lot of money by selling a lot of your goods, your site has gone down because it got overloaded. Okay, that's the worst thing that can actually happen if you're an online business. Okay, but dealing with unpredictable workload is a way of life. You cannot actually control how many users on the internet suddenly decide to visit your store just because you are a popular product or whatever. Okay, so you need to be able to deal with that. You want high performance and low cost You want to automate resource management as much as possible. Okay, you cannot have 10,000 administrators to manage 100,000 machines. Okay, the cost of actually hiring all these people will go up. What you want is to be able to automate a lot of the tasks and have a small set of core people that manage with larger and larger facilities. So you want to use a lot of automation. So virtualization allows you to automate lots of things as well. And energy efficiency is another big problem. Okay, when we talk about green computing in the guest lecture, this will be talked about in a lot more details. I already said servers consume a huge amount of energy. They consume electricity. There's electricity to cool off these data centers. That gets very expensive very quickly. So, and you want to be green. Okay, there are data centers that have started using on-site solar, for instance. Okay. Apple claims that all of their data centers are now powered 100% by solar facilities. They don't actually go to the electric companies to get electricity. They generate their own electricity. In fact, they have actually 100-acre land next to their data center that just has rows and rows of solar panels. Okay? 100 acres of solar panels to probably power 10 acres of servers. Okay? Now you can imagine when you have these renewable energy sources, there are additional challenges. Renewable energy is not going to be predictable. There is no solar generation in the night. Okay? You can't take your server down in the night saying, sorry, no electricity. That doesn't work. Okay? So if you say, I want to be green and I'm going to use solar or wind power, you have to have one more problem that you have to deal with. What happens if there is no wind today? Or it's a cloudy day and my solar panels are not generating as much as yesterday. Users are not going to say it's cloudy, so I'm not going to use the server. Right? They want to use the server independent of how much you can generate. So you have to deal with this problem. You have to have a local energy storage so that if in the night I can keep the servers running or I switch over to the electric grid. There are many things you have to do. Okay? It makes your design more complicated. And when we talk about green computing, you can ask more questions at that point because this topic will be dealt with in more detail there. Okay? But here we'll only talk about data centers, not the energy aspects of it. Okay? So typically, the other thing to keep in mind, the reason I was actually talking about all this is when you have this very large data center, reliability becomes an important issue. Okay, when I was talking about fault tolerance, I said as the number of machines in your system grows, the probability that any one machine is down at any time is going to be at least one machine. If any is down at any time, is going to approach one. Okay, because if you assume components fail independently, okay, then if the probability of a failure is p, and the probability that any one component fails is 1 minus p to the power n. And as n goes to infinity, that probability goes to 1. So you don't have to read all of this, but this is just saying if you take a typical Google's data center, what kinds of failures do you expect and what can go wrong? So power servers may overheat, the power distribution unit for a rack may go down. Okay? You may decide that you want to move a rack from one location to another for a variety of reasons. You may decide you may want to rewire some of the cables because some cables are old or they are failing. So you have to take this as planned outages. These are not failures. You take machines down because you need to do some maintenance. You may actually have racks, entire racks failing. You may have network maintenance. Router may go down. Servers may be up, but router goes down. No network connectivity. Yes, machine is unreachable. Your routers may fail. Machines may fail. Disks on the machines may fail. So any of these things can happen that cause systems to be down. Okay, so what that says is if you have very large servers or data centers and you're running applications, you better design your applications to tolerate problems like this because they are going to be a daily affair, not that once in a while some of these problems are. Okay, so you want to have replication, you want to have fault tolerance, you want to have automatic failovers, all of this built into the application. Okay, otherwise, you will have lots of availability problems. Your system may see outages every once in a while. Okay. Now this is just a pie chart of the cost of running a data center, and the only thing I'll show is that this red part of the pie chart is electricity bills you're going to pay. You will see that that's a significant part of building and operating a data center. Okay. This is actually a small data center, only $1 million of electricity. Larger data centers might have tens of $millions of electricity bills that they incur over a period of time. Okay. So this basically leads us to the discussion on cloud computing. Okay. So I just give a very quick overview of what is a data center, what's the scale. Data centers are some of the largest distributed systems you have today in some shape or form. Okay. So it's instructive to see what kinds of challenges arise at this extreme scale. Okay. So we'll now talk about cloud computing. Okay. That's basically a good segue from going from data centers to cloud. Okay. So we'll say what does cloud computing mean? We'll define it. We'll see that there are different kinds of clouds. We'll try to categorize or classify the different kinds of clouds, and then see what kinds of things you can do with it. So why have they become popular and so on. Keep all this in mind because your next assignment actually requires you to use the cloud in some shape or form. Okay. So what is a cloud? What does cloud computing? Okay. One way to think about this, what is a cloud? Is it's a data center, okay, like any other data center, with one special way to sort of use it. You can go and request machines from these data centers on demand, okay, as and when you need it, and you can pay for them based on what you've used. Okay, so one way to think about it, it's a pay-as-you-go data center. Okay. You can rent machines and storage from this data center. So if you a developer want to set up, let's say, a website, rather than buying your own server, okay, and then setting it up, you can simply go to a cloud data center and say, I want to rent a server. And you can pay by the hour, literally pay by the hour. I mean, some machines cost 5 cents an hour. Okay, you want to run something for 5 hours, you will pay 25 cents. That's it. You want to run it for a month, you may pay $50. Okay, so it's a data center that rents you resources. Okay, and you basically pay based on that. So it's a very different way of thinking about it. Rather than buying and building your own, you rent and use as you go. Okay, so that's basically what it is. So it's remotely available, pay as you go, and it's shared. There may be other users also renting as well. Okay, and some users may have been mapped onto the same physical machine. So it's a shared infrastructure rather than when Google builds a data center, they own all the machines, they own all their applications. Okay, when you go to a cloud, there may be 10,000 customers that are all sharing all the resources of that data center. And the cloud provider has actually rented all those machines out to the end customers. That's the way to think about it. Now, you probably have encountered cloud services already. Okay? So there are different types of clouds. They're referred to as software as a service clouds, platform as a service cloud, and infrastructure as a service cloud. For your lab assignment, you are going to actually use this type of cloud, an infrastructure as a service cloud. But as far as what you've used, you probably have used some of these already. Okay? Gmail is an example of a software as a service cloud. Okay? The cloud service rather. It's a cloud-based email service. Okay? Most Gmail is free, so you're not actually paying as you go, but you don't own your mail server. Okay? So you are renting a mail server, you're licensing a mail server, Google runs it for you. Okay? You just basically get mail service from Google. Salesforce is another example. Whereas Google Docs is an example of Office running on the cloud. Microsoft now has an Office in the cloud offering where you don't actually have to buy Microsoft Office. You basically can rent Microsoft Office and they will run the application on their servers and you can get storage space on their servers. Okay. So that's again rent versus rather than buying Office and installing it locally, you just rent it and you use it remotely. Okay. That's basically. So this is referred as a software as a service cloud where you have hosted application. You may pay for these applications on a monthly basis. Some of these services may be free and they are managed for you. You don't actually have to go administer any of these things. Okay, you just go as a user, you log in, you use your application. And that's the top level of the cloud. Next layer is referred to as a platform as a service cloud. In a platform as a service, you basically get the hardware and some software on which you can run your own application. Okay, so Google App Engine is an example of a platform as a service cloud. Microsoft Azure is another platform as a service cloud. Okay, so here you go and you rent something, and what you get is a machine and software installed on that machine. And then you can you write your code and you deploy it on the machine, and then it's managed for you, and you get a bill every month saying this is how much your application used, these are the number of requests, so your bill for this month is $15, and that's what you pay. So that's platform as a service. At the very bottom, you have what is called an infrastructure as a service cloud. These are called IaaS cloud. This is the lowest layer. Okay, here you only rent bare bone machines. You can rent hardware, no software. Yeah, so you will basically get a bare bones machine. You decide what OS to run on it. Yeah, you install whatever OS you want. You install whatever applications you want. So you do all of that. You are only renting hardware. Yes. Okay. So Amazon's EC2 cloud is an example. There are many companies that provide similar service. So what you will be doing for your lab assignment is you will actually go and get a server from the cloud using cloud accounts he will give you. You will go get a server from the cloud, and then you will go through the process of installing an OS on that server, and then you will run your lab code on that server. So you will do it all. Okay, what the cloud provider is going to give you is only bare bones server and some disk storage. Okay? In this case, you get servers and some software pre-installed for you. In this case, you get server, software, and applications pre-installed. Okay? So as you go up the stack, more is done for you by the cloud provider, and you do less, and you have less control. As you go down the stack, you basically only rent sort of fewer and fewer things, and you end up doing it. Okay? So depending on what application, what you want to do, you may get these different types of clouds. Okay? So when you hear the term cloud, you basically have to keep in mind that there are these different types of clouds. The clouds are not all the same. They can be different depending on what they're trying to do. Yeah. So I'll spend a few minutes and then we'll continue this next time. So here is an example of a platform as a service cloud, which is Google App Engine. So Google App Engine essentially is a Python-based platform where you can develop your application using Python, and you can just deploy it on their server. Okay, so they provide you Python, OS, server, storage. All of that is provided to you by them, and they will deal with serving requests and all of those things that are needed for you. Okay? This is not necessarily based on virtualization. You just give them some code. You can have Java clouds as well. You can think of a J2EE application that you've written and just show up with some Java code, and they will run it for you. Okay, so basically they provide the entire software stack and the hardware needed to run your code. Okay, that's what in Google, this is Python based. There are other clouds that will do Java based. Microsoft Azure cloud uses .NET. Okay, write .NET applications and run them on that cloud, for instance. Okay, so and then what the cloud technology does is it automatically figures out how many threads to allocate to your application. If workload goes up, it will automatically replicate your code on their multiple servers, partition. All that is handled for you by the cloud provider. You don't tell Google when you give them the code saying run it on 3 machines. They figure that out based on what workload your application sees, and they bill for it based on what you are doing. Yeah, so it supports Java and Python. This is infrastructure as a service cloud. This is what you will be using for your lab assignment as well as an exercise. So here, as I said, you rent bare bone machines and you rent storage. Okay, this table actually shows you the different kinds of machines that you can rent. Okay, so you can basically say, give me a small server, a medium server, an extra large server. There are literally 8 or 10 different kinds of hardware servers available on Amazon. And each of them has a different price you pay. Okay, the smallest one, you literally pay 2 cents an hour. Okay, so if you rent such a server for your lab and you run it for 5 hours, we will have to pay 10 cents to Amazon. So you don't actually pay the bill for your lab, we'll take care of that. But that's what we will get billed. Okay? You decide to go for a large server, you pay $2 an hour, because that server may have like lot more cores, it may have more RAM, it may have more storage and so on. So you have to decide as a developer what kind of machines you need for your application. You can rent them for as little or as long as you want. And at the end of every month, there is a bill to be paid based on what you have used. That month you didn't use anything, you don't pay anything. Okay, you used a lot, you pay a lot. So that's the way it goes. So what this avoids is, as a developer, you don't have to buy a stack of machines upfront if you don't know whether you need literally one machine or 10 machines for your application. Many times you may not know. When you start off, you may need very little, but if your application keeps growing in popularity, you may need more and more. Here, you can literally provision a machine in minutes. You can say, give me a machine, and 5 minutes later, that machine is ready for use. Because they have just installed a virtual machine, They bring it up and they say, here, go use it. Okay, so you can get machines in a matter of minutes rather than placing an order and having the machine show up 2 weeks later. Okay, so renting is much faster than buying because they have already pre-populated the servers for you. Okay, so that's an infrastructure as a service cloud. In this case, this is Amazon. There are many other service providers that do the same. Okay, so a couple of slides remaining here. We'll continue that next time. Okay, so for today, let's just end it here.